And Scott will lead the discussion on how to connect the different scales in the simulations. Take it away.
All right. So we are going to have a little discussion now about connecting different scales, which can mean lots and lots of things. And we just had 2 excellent talks this morning that generated a lot of discussion. So it's also fine if we want to, continue talking about some of those topics. But I'll just, thank you. Quickly outline some possible discussion topics that we came up with, and then Scott is going to have a couple more introductory slides, and then we do have a few slides that were contributed as well. So this is just to kind of give you the overview of what we were thinking about covering. So we broke this down into connecting galactic scale simulations to black hole scales, which has many components. We'll have a couple slides on that, but this involves things like host galaxy, how do they influence black hole accretion and hardening, when and if there is a final parsec problem or a final kiloparsec problem. We had some discussion earlier this week about the extent to which the dynamical friction regime of InSpiral might be more of a limiting factor on the merger time scale than originally thought. And then also the role of AGN feedback in black hole evolution, and how that affects binaries differently than single AGN, and how stellar feedback might play into this. So those are just some ideas to get percolating in everyone's minds, and we can come back to those later if we want. And then the other category we came up with connecting GR to Newtonian scales. So Scott will present a couple of slides about that. And then also dividing this into observational prospects and limitations for trying to connect these scales, and then also just specific numerical techniques. So I think I'll hand it over to Scott for the rest of the intro.
We do acknowledge a bias. We're, I guess, talking about the black hole case, but we certainly have been, always talking about connecting to stellar binaries. So we don't want to exclude the stellar binary folk, but so for the AGN and massive black hole case, they suffer, huge timescale, spatial scale problems. So here, this is just a diagram that Gaspari and Tombesi and Capi generated that shows how black hole feedback can then, be launched in these ultra fast outflows, these UFOs that can launch material out to galactic scales that then cool down, so that these are ionized hot outflows, but then they eventually cool and fall down as rain at these galactic scales that then refeed the AGN. And so an AGN can actually go through hundreds of these cycles over a Hubble time. And so how does this rain feed the black hole? Is it a chaotic accretion kind of phenomenon? How does that affect the observables? How does that affect our understanding of how black holes feed, grow, evolve? And then, and then this is just a single AGN case. We're talking about binaries. So how does the binary complicate this picture? So it's really, this is 9 orders of magnitude that this cycle covers. And so it's really challenging to really understand this. Also, there's a temporal problem too. So these black holes can evolve and merge on timescales that are blips and also span human lifetimes, right? So we have to be aware of these vast timescale differences, and we have to also, if we're aiming to see these things in gravitational waves or light, then we need to be cognizant of the fact that these observations take periods of time. Also, these observations are using instruments that have also finite lifetimes. So, what are the optimal instruments, pointing strategies, wavelengths, frequencies that we need to look at. For instance, like eccentric. So do we expect the binaries to be equal mass eccentric binaries at the time that we observe them? What's the likelihood? If they are, eccentric orbits are bursty, right, in gravitational waves, and maybe in light. And so that burst may not happen when we want it to happen. So how do we deal with that? And then Alessandro Lupi, do you wanna talk a little bit about this slide?
Yeah, Alessandro Lupi here from the University of Milan. Well, actually, about the multi-scale problem, of course, well, many simulations today, of course, follow different scales. Of course, we cannot run a single simulation that goes from the cosmological scales where galaxies merge and form down to the scales in which black holes accrete. And also, when you split the problem with on different scales, also the physics included in the simulation is completely different. So I think at the moment we still have a lot of problems in joining the different scales because many processes are neglected in some cases and in some large scale simulations and not in small scale one. And so matching the boundary conditions of these different studies is still problematic. So one question for all of you is, how can we improve in this sense?
Yeah, like what are reasonable initial conditions to start with? I think that is a really good question.
Yeah. So this slide is along similar lines. Anish Sivasankaran, do you want to talk about this slide?
Yeah, thanks. Anish here. So yeah, this is a recent study where we basically looked at supermassive black hole accretion in the context of galactic scale simulations. So here we basically used like galactic or isolated and merging galaxy simulations or a few gigayear time scales, and basically use a ISM model which basically models the multi-phase structure with an explicit implementation of stellar feedback. So we have a very realistic ISM like shown in the top left plot. And if you look at the accretion rates in these simulations, we find that black hole accretion works in a qualitatively different way, like seen in previous simulations. We have these extreme stochastic time variability over a few mega year time scale where the black holes basically switch between an on and off state over these time scales, and mainly due to the turbulent and clumpy gas clouds in the ISM. And if we use these methods to look at how accretion works during galaxy mergers, where we can look at the accretion rate when the black holes merge together, we see that if we use these models, we see a much smaller enhancement compared to what was predicted using previous simulations, like the ones used in Illustris and Illustris PNG. Yeah, that's a brief summary.
And just to clarify, that you mean a smaller enhancement due to merger-driven dynamics? Yeah.
Yes, we compare them, we see something like an order of magnitude discrepancy between the predictions of the two models because of the strong stellar feedback in these simulations. So it's really important that we incorporate these multi-phase structure and the impact of stellar feedback carefully into these galactic scale simulations to accurately study black hole accretion.
Right, thanks. So yeah, I guess sort of building off of those two slides, one question I would pose to everybody is, how well do we really understand the feeding conditions for these small scale simulations? To what extent the uncertainties in connecting the actual fueling of galactic nuclei down to the smaller scales going to affect how we're thinking about black hole fueling. I don't know if anybody wants to jump in on that.
Maybe this isn't helpful. It's a question, not an answer.
That's
but
great.
One thing that came up, I think, when we were talking a couple of days ago about the semi-analytic models, trying to predict gravitational wave signals, was this issue of what are the initial conditions you start from in terms of frequency, mass ratio, and separation. And I'm still trying to understand how we connect up these simulations with those models and what's really the best and most trustworthy snapshot to take insofar as these, are obviously very expensive, amazing simulations, but there's only so far that they are resolved. So on what scale do you think you would say freeze the population from here, and then you're better off using some analytic model to integrate them forward? Like where should we stop in the simulations based on resolution, for example, or subgrid physics that you do or do not believe?
You mean in terms of like at what scales, or are you talking about a time evolution thing?
I guess it would seem to me more of a spatial scale issue than a time scale issue, but maybe that's because I don't know.
Yeah, so I mean, I think we are not really at there are starting to be some more of these, super refinement, super Lagrangian refinement schemes, hyper refinement schemes that get closer and closer to sort of the gas capture scale of the black hole. These, I think, Anish, are getting down to maybe just a little below 100 parsec on average, maybe a few tens of parsec. And then, of course, the more you try to zoom in real time, then the shorter time scales you can simulate. So that's what, Anish is kind of taking a hybrid approach here of not zooming in too far and simulating for giga-year timescales. But yeah, I think the schemes we're using for black hole accretion are definitely a major uncertainty in these simulations in terms of how much of the gas that's inflowing through our resolution limit is actually ending up on the black hole. I don't know if Alessandro or anyone else.
Yeah. And I'll just add to that, what about the evolution of the orbits that you're getting as well, like how quickly they're getting to whatever radius they are at is the other thing I would include. But
okay, so you're talking about like the actual the black holes evolving down to the resolution scale, whether or not the resolution limits are affecting the black hole dynamics.
Yes, all of the. I'm talking about all of the above. I guess.
All of the above.
Yes.
Yeah. Yeah. Does anyone want to speak to that? I can give my 2 cents, but this also isn't just supposed to be us talking.
I just have a, yeah.
I think at the moment the problem is both on spatial and time scales in general, because when you start from the galaxy scales, of course, we are not able to resolve the interaction on small scales, and so also the dynamics that brings the black holes together is not very accurate. So that's why, for instance, you have to include additional subgrid prescription to correct for missing physics. But also in terms of time scales, because when the two black holes pair together and become a bounded binary, then the time scale of the evolution of the binary is short compared to what your typical time step in the simulation. And if you reduce the time step in order to follow the dynamics accurately, even if you have the resolution, then everything else will look like frozen. And so your simulation will waste a lot of time only to keep track of a frozen medium outside. So this is...
Elena, did you have a comment or as well? Sorry, I didn't see the hand over here.
So where do you think we should stop then? And the large scale evolution and then merge with the small scale one, where it's the safest or the best that we can do at the moment?
Well, I think starting from the galaxy scale simulations, the ideal to me would be to at least get down to the scales at which the binary potential dominates is the most relevant contribution to the local potential in the region. So when you start to have a circumbinary disk and the self-gravity effect due to self-gravity of the disk becomes less important. In that case, at least you can track very well the inflows from the large scales and use those as boundary conditions for the evolution on smaller scales. I think that's what we should aim to at the moment.
Right.
And with the hyper-Lagrangian refinement, this is becoming achievable.
Right, right, but only just, right? It's still pushing the limits, especially for longer timescale evolution.
So I had a question about this particular simulation and then related ones. So the M dot black hole, what is your sync radius and what is your sort of minimum mass particle that you're including in this?
Sorry, what radius?
You define an M dot BH.
Yes.
What radius is that measured at? Is it 1 parsec, 100 parsecs?
Yeah, so so we use the Bondi-Hoyle accretion prescription, and to calculate the gas properties, the radius is typically around a few tenths of parsec. So we estimate the gas properties at that scale and then calculate the accretion rate.
And so you said you use Bondi, but that's for a one phase and you have a multi-phase medium. So what is your mass resolution? And
the mass resolution is around 2000 solar mass. That's the smallest gas cell we have in the simulation.
So, I'm sorry, I didn't mean to interrupt you. You were going to say something else.
It was not clear to me, like, what do you mean by the phase dependence in the?
well, the Bondi rate depends on a density. And if you have cold molecular clouds in a hot gas, the hot gas accretion rate is appropriate for Bondi. The cold molecular clouds might be too small, so you shouldn't be using Bondi. And I don't know how one calculates an M dot in that case.
Yeah, that's a problem here. Like, it's not very clear if Bondi prescription is completely accurate or appropriate when we have this extreme cold density gas clouds. But I think if we are only resolving at around 100 parsec or a few tens of parsec scale, it might be still okay to use the Bondi prescription.
Yeah, I would add to that I mean, yes, we're not claiming that this is the actual accretion rate onto the black hole, right? But it's more of a comparison of how the Bondi, a Bondi-like accretion rate would vary over time from you're averaging over all of these, heterogeneous density media. But I think one of the interesting things that comes out of this is that it is very strongly dependent. So you do actually have rapid variation between phases where it is a pretty diffuse low density medium owing to local stellar feedback and when it's actually a more dense medium. So it's more illustrated in that sense. Magda?
So I'm worried about the accretion rates as well. I think this model here is similar to what Illustrious does, is that right?
In terms of the accretion prescription, yes.
In terms of also how the total accretion rate is calculated. So I think Illustrious also measures some sort of gas density at some radius away from the black hole location. And when I think about this, and it scares me, I always remember that there is some evidence that Illustrious actually does arrive at a fairly reasonable black hole mass distribution at redshift 0, right? Mm-hmm. So I wonder if maybe at times these models are really uncertain and not physical, but if they are over long time scales tuned in such a way that they arrive at the right solution, then maybe in the end we don't have to worry too much about how they get there. Because we care about what the black hole mass distribution looks like. Well, at least for gravitational wave background calculations, we care about the end results. Mm-hmm. And if we can get there and we can have sort of physical accretion rates along the way, we might be able to arrive at a at some physical binary distribution.
Yeah, I mean, I would say that, sorry, Julian, I just will respond directly to that. But certainly in terms of cosmological populations, yeah, a simple Bondi model and cosmological volume seems to produce the local black hole population pretty well, right? So on average, we're clearly getting things mostly right. But I think that the interesting question in my mind is, if black hole accretion is, really more like this than like this, then what does that mean for, EM observability, for fueling these, sub-resolution accretion disks that, we're spending so much time talking about at this conference. So I think I'm not worried so much about the average black hole properties. I'm worried about the details of how black holes are fueled. Right,
yeah.
Julie?
I'd like to respond in part to this point, and in part to generalize the remark that Sturl made just before, which is there's, as you've emphasized, a very wide span in length scales here. And so you might expect that there would be different physics every time you change by a significant amount, every decade or two of change in scale. And in fact, we've already heard several examples of this in the past few days of this conference. One of them was the issue that Sturl raised about the inhomogeneity of the interstellar medium. Another is the discussion a couple of days ago about the effects of radiation forces on dusty gas and how that might actually expel the majority of the stuff that came into sort of parsec scales and not let it proceed any further. We've also thought about, briefly, the possibility that the accretion disk inside that, wherever the gas is actually captured, breaks up into stars. And there's a question of how much remains in gas, and so on. So this is probably not going to be a situation where there's an easy extrapolation from larger scales to small without qualitative jumps in terms of new physics.
I completely agree. Yeah.
We have a question online.
Oh, okay.
I don't know how to navigate. Tamara, would you like to pose your question, please?
Yes. Can you hear me?
Yes.
Yeah, I will also add to this list of concerns that we should also worry about the effect of radiative feedback from accreting massive black holes, in addition to the stellar feedback, and we should worry about them on larger scales when we expect dynamical friction or gas dynamical friction to play an important role. This is basically related to my talk on Tuesday, where I said that we see dramatic changes in merger timescale and coalescence rates when we actually implement the effect of negative gaseous dynamical friction. If indeed nature operates in a similar way to what we see in our smaller scale models, so if negative dynamical friction operates that way, I think that we should be careful and study this effect to see if it really, even in presence of triple massive black holes that may drive black holes to merger regardless how they stall, any mechanism that drives black holes to smaller separations will have to work against negative dynamical friction if it really operates in a way that our models show us so far. So that is my 5 cents. I, as probably everybody in the conference, wish binaries to merge so that eventually they can coalesce and be observed as gravitational wave sources. But that optimism to the side, we should understand these effects. So yeah, that's my cautionary note. Thank you.
Well, I wanted to add something about what we said earlier about black hole accretion, I think in general there is another aspect that is black hole feedback. In all the large scale simulations, actually, you have a lot of knobs you can turn. So you can change how accretion proceeds, so you can rescale your accretion, but also feedback, because otherwise the black hole population cannot be found to match the local observations at least. Mm-hmm. And there are a lot of free parameters, so it's not only a matter of choosing the right accretion model, but also the feedback. And going back to what Tamara said, yes, I totally agree that also radiative feedback might be extremely important, especially in the regime of when dynamical friction is relevant for the orbital decay of black holes. We should also consider, though, that on large scales, not at kiloparsec, but on larger scales, when the density of the gas is lower and radiative feedback from a black hole might play a more important role, the black hole is still embedded in the galaxy nucleus of its progenitor, of the galaxy host it was hosted in. So it might be that in that case, the dynamical friction goes back to be more efficient because of the total mass of the system that is much larger than the black hole itself. And in particular, because of the relatively poor resolution we can achieve in these galaxy scale simulations, I think the effect of radiative feedback is probably most of the times unresolved so far. Of course, if we are able to increase the resolution, we could resolve it, but we are not yet there yet, I think.
Yeah, I would also just echo the importance of directly resolving dynamical friction around a galactic nucleus containing a black hole that is continuously being tidally stripped. I think that's a problem that we haven't really fully solved yet in terms of directly modeling it. So we have another online question from Shin, and then we have a whole set of other slides on connecting GR to Newtonian scales that I would love to get to. So maybe we can jump there next. Shin, do you want to go ahead?
Yeah, thank you, Laura. So I think a problem in terms of connecting the vastly different scales is that we do have a broad general agreement in terms of observations of AGN phenomenology, the luminosity function, the overall cosmic evolution, and the merger-based model, right? So the merger trigger quasi-activity with feedback and so on. But I think the problem is that we don't know, as Laura already pointed out, we don't know the details such as the mass ratio of a possible binary and how the accretion and the binary formation are linked together, and how I think that's the relevant, that's the key unknown if you care about gravitational wave predictions. And one possible direction I think that we need to make progress is we need more observations at higher redshift, where a lot of this merger, induced activity is happening. Because at least locally, if you look at AGN population, like a majority of AGN, like at least low luminosity, doesn't have to have anything to do with mergers at all. At least that's the general consensus of these population studies. And it's not entirely surprising, because for low luminosity AGN, you don't need merger at all. What's unknown really is, I think, the relevance of merger at higher redshift, where perhaps you have very different host galaxy properties, the ISM, the gas conditions that I think need to be tailored. The simulations need to be tailored to these particular properties, and hopefully, as we have more observations, like the system that we can directly resolve at higher redshift, like redshift 2 and above, hopefully, so that you can, at least connect your cosmological simulations with observations hopefully at parsec or like kiloparsec scales and maybe even sub kiloparsec at those time, because those are the presumably the progenitors of the binary system that are going to evolve into the PTA sources at redshift 0. So that's my 2 cents.
Thank you. Yeah, lots to do on the observational side. So maybe now we can move on to GR to Newtonian scales. Sorry, Scott, we didn't leave you more time.
No. I'll just, so how do we connect? So there's so much work in the Newtonian side of things, and so we'd love to see when we can kind of connect the two. And so yeah, so when is GR important? You know, is it ever important in the binary disk problem? So we've kind of explored how things change with separations. So the different curves are at different separations. Blue is 100, then 50 is green, 40 is red. And so we can also turn off the higher order terms of the post-Newtonian expansion that we use for the space-time. So 1 PN is more Newtonian, 2.5 PN is more relativistic. And so you see that, you know, at around 40 M separations, you start to see the change in the torque on the gas. So this is just a 2D hydrostationary torus that's in a binary spacetime, and we're measuring the torque. So we're seeing at around 40 M separation that the torque changes. If you do an MHD simulation and you turn off the higher order terms, the beat frequency of the light curve seems to diminish in strength. So this is the, you know, this is nonlinear dynamics, so we don't know exactly why, but the idea is that maybe the extra terms enhance the torque that drives gas into the lump, and so there's more modulation there in the lump region. So maybe as you get closer to merger, the torques increase and you get more interaction between the black holes and the disk. So well, you know, what are the best best things to measure to explore when this transition happens? I'm interested to hear what other people think. We've also, some of these GR problems also suffer a timescale problem. We don't run them long enough to maybe reach a steady state. We've now run them for, I think, 500 orbits. We seem to match now the Newtonian J dot net curves, except we measure something a little bit lower than what is produced in Newtonian codes. So the Newtonian level is this dotted line, which is around 0.7, I believe, 0.68. And we measure around 0.5. So it's still not at the threshold that you would get in spiral. So it's still out spiraling. But yeah, this is just showing that maybe there are other things that we need to include that have, you know, some effect on this thing. So yeah, and then there's triples.
Oh, yeah, I put this in there like in case we needed more stuff to talk about, but if we want to talk about, you know, the previous slides, if there's discussion about that, we can not jump topics again. Anyone have?
Maybe I have a quick one. I wonder how far you can push things with the Vita-Paczynski potential, which is very easy. Like how would the 20 M look like if you use Newtonian with a Vita-Paczynski?
Yeah.
I don't know if you've compared that.
What would the 20 M separation run look like with the Paczynski-Vita potential? Is that what you asked?
Yeah, you compared things with one post-Newtonian expansions.
Yeah. I mean,
another way to do this is to use Newtonian simulation, but with the Vita-Paczynski potential on each black hole, which is very easy to do.
Yeah.
Just wonder if you compare that to the
Well, yeah, 1pn is pretty Newtonian. Okay, well, Alberto knows better than me, so. Yeah.
Hey, Alberto, you weren't mic'd. Maybe can you repeat that with the mic?
Or maybe you want to answer, Scott.
No, please. I actually don't.
I mean, the Paczynski beta gives you the wrong rate of precession at 1pn. So for, doing the post-Newtonian calculation, you shouldn't use it in any way. I mean, yes, gives you an idea what's the precession, but gives you the wrong precession. So doing a 1pn expansion is as easy as using a Paczynski beta and gives you the correct 1pn precessions. You should do that.
So Paczynski-Weta gives the ISCO right, but as you say, it gives the 1pn wrong with the vague potential, which is equally simple. Doves gives the 1pn right. But vague, W-E-G-G.
Yeah, Scott, can you show the next slide again? I just want to make sure so could you describe, maybe I missed it, but the setup is basically you have binary and you have a torus around it.
Yeah.
You have magnetic field natural, putting, and then you let it evolve for only how many orbits, how long?
Okay, so this is 3D GRMHD simulation, circumbinary disk only, but it shouldn't matter for JDOT. How many? Oh, did I not include the extra slide? No. Sorry. How many orbits? We got 500 plus orbits. So this is mass enclosed. So this establishes a steady state. M dot is out, is flat. So we're in pretty good mass and flow equilibrium. We haven't run the 50 M separation, 100 M separation as long as this large case. So large is just a bigger disk. It's like the situation we used in 2012, but just with a bigger mass reservoir. So because we found that actually the disk was draining over the time span of and this is with us. We analyzed these runs with a NASA intern last year. So she's unfortunately not working with us any longer, but she made really good progress. Do you want to go back to JDOT? I don't know.
Yeah, okay, thank you. It's impressive you can do this. Yeah, thank you.
Further response from online.
Yeah.
Manuela, do you want to unmute yourself?
Did you call me?
Yeah, go ahead.
Oh no. Okay. So this was in relation to the previous comment from Alberto that we shouldn't use 1pn. Indeed, we don't. I mean, the study that Scott showed is to really emphasize the differences among these PN terms. But the PN that he mentioned there was referring to the space-time that we were using, the space-time constructions, not the trajectories. The trajectory are up to 3.5 PN. So we capture precession.
Alberto here. So no, I wasn't meaning for sure that you were using 1pn, Scott. Well, I have a question for Scott. In this large disk with A100M, did you try to match this to to translate this into a, let's say, standard alpha simulations, so to to do the map between the two? Because you say, I mean, you said that you find the out spiral, but the J dot is a bit different. But that, what do you compare here? You are comparing with a disk with aspect ratio 0.1, or you can maybe get to map the one into each other. So we see how a certain alpha translates into a simulation of this type.
Yeah, I think we need to do similar initial conditions maybe as the alpha disk community does. Here I was trying to kind of just get as close to this setup and change the separation. note that the curves look different in these runs, probably because it's not in mass inflow equilibrium yet. So, you know, we don't have the J.net flat yet. So you still are, you know, this one's actually getting close. This one still has some way to go. But yeah, it would certainly be interesting to, yeah. Oh yeah, and H over R is 0.1. Yeah, so we cool the disk, so it's 0.1. So it's a moderately thick disk. But
and you haven't sort, let's say, Julian, don't feel
it's ideal
insulted
gas.
by this. You get a sort of effective alpha for the simulation.
Yeah, I mean, it's a function of R. It's more or less what Julian showed or Roger showed yesterday. That was a slide that Julian contributed. I think Julian. That was Jaming's, but like we see similar things.
Okay.
Done, what? Yeah.
If you describe the time averaged, vertically integrated, et cetera, ratio of stress to pressure, it's a function of radius, right? But the general level is in the few tenths range. Okay. And particularly near the inner edge of the circumbinary disk, which is probably where it makes the most difference. Okay, thanks.
We had another hand on Zoom that disappeared. Alex, do you still want to ask a question?
Actually, yeah, so I think this was cleared up by just the previous comment from Zoom. I was just thinking about the periodograms, and one thing that has always made me a little unsure about how to interpret those is just because the orbital separation of these black holes is changing over time. I'm a little worried about defining or measuring these periodograms in terms of the binary orbital frequency. But I think it was still, if I remember correctly, a fair comparison, at least changing the PN order. I guess if the trajectory was the same, that wouldn't actually affect that particular comparison. Yeah.
With the different
in some of our published papers, look up basically it's the Bowen et al. Series. We have examined the Fourier spectra alternatively in terms of absolute time and in terms of orbit count when the orbit is in fact inspiraling.
Right, yeah. You do see some drift in the power spectrum, the peaks in the power spectrum.
Looks like we have one more hand on Zoom. Hey, go ahead.
Manuela?
Sorry? Did you?
Your hand is up. Do you have a
Oh,
question?
I'm sorry. I didn't turn it and I didn't put it down.
Okay.
Okay, then we have, Hang, do you want to go ahead with your question?
Shall I read my question? Oh, okay, many thanks. So my question is really simple. Since the 4 subpanels you show in the bottom of this figure, it seems the integrated gravitational torque is gradually diminishing with your larger disk. Is there a simple explanation for this part?
Oh, the J dot rad? Rad?
The yellow line, the integrated gravitational torque. No,
grav. Yeah, it's a gravitational torque, yeah. Oh, why is it getting smaller? Oh, for larger separations? I think it's just, it's not in equilibrium yet. I mean, you notice that it's not, this plot cuts off a little bit further out than ours. Yeah, I guess ours is a bit larger. It could be because of the, I don't know, different gravity that we use. Could also be we have more mass due to, no,
It's a generic feature. J dot, the T greater than R gravity is an integral quantity. The torque density per unit radius oscillates in sign. And so that's what you're seeing.
I don't quite.
Yeah, well, the position of the oscillations is fixed in terms of R over A.
So I would not put a lot of confidence in the relative amplitudes of these as a function of separation yet. I think these still need time to kind of equilibrate. So I just wanted to advertise the fact that we're looking into this, and if anyone has any comments on the strategy, I'd appreciate it. But yeah, I would really kind of just look at that one and compare it to maybe that one right now. But yeah,
I think there are rather interesting discussions. We probably should move on to the next one. Sure. Last one.
Okay.
I was wondering if anyone's actually done a convergence study on these torque signs. So actually just varying resolution and seeing if there's a significant or a trend up or downwards, and maybe it's even goes down, goes up again. I think it could be interesting to look at that.
Yeah.
It's a great segue.
Yep.
All right.
But the answer is yes.